The topics covered in this video are first a review of hybridization, the hybridization of nitrogen and oxygen, molecular orbital theory, and drawing chemical structures. sp3 hybridization involves the mixing of an s orbital and 3 p orbitals to form 4 new sp3 hybrid orbitals. So if we're looking at carbon, you take the 2s orbital in carbon and you mix it with all 3 of the 2p orbitals, and out you get 4 of these hybrid sp3 orbitals. So the hybrid orbitals are a mix of the s and the p orbitals. Whenever you have sp3 hybridization, you will always have 4 sp3 hybrid orbitals, because the number of orbitals that combine to be hybridized equals the number of hybrid orbitals formed. So if we mixed 3 p orbitals and an s orbital, that's a total of 4 orbitals. So we get 4 hybrid orbitals out. And again, this notation indicates you used 3 p orbitals and just 1 s orbital. So when you have something that's sp3 hybridized, it's going to have a tetrahedral electron geometry, where here all of the new sp3 orbitals that you formed are going to be pointed towards one of the corners of a tetrahedron. So when you put it all together, this is what it looks like. If we take methane, methane is a carbon that's bonded to 4 hydrogens. It's sp3 hybridized, so it's going to form bonds with hydrogen by overlapping an sp3 hybrid orbital with hydrogen's s orbital. Hydrogen never has any hybridized orbitals because all it has available to it is that s atomic orbital in the first shell. And so this is how methane forms the 4 sigma bonds between carbon and hydrogen. And remember, sigma bonds just refers to a bond that is cylindrically symmetrical, and all single bonds will be sigma bonds. When we go to sp2 hybridization, you're taking the s orbital and now just 2 of the 3 available p orbitals, hence sp2. Now, I mentioned the number of orbitals in equals the number of hybrid orbitals out, so we put 3 in, and out we're going to get 3 hybrid sp2 orbitals. That means this p orbital that didn't get mixed in is still hanging around. It's going to be unhybridized, and it will be available to form pi bonds. So anything that has an sp2 hybridization will have a trigonal planar geometry. So this is a representation. If you just have a triangle here, then the sp2 hybrid orbital would be pointed at the 3 different vertices of the triangle. Now if we look at ethene, sometimes called ethylene, so both of those carbons are sp2 hybridized, which means they each have 3 sp2 hybrid orbitals that will be used in bonding, and they each have an unhybridized p orbital. So the carbon-hydrogen bonds are all formed by an sp2 hybrid orbital on carbon overlapping with the hydrogen s orbital. So there we have the overlap forming those carbon-hydrogen bonds. Now that means that we have to account for the double bond between the carbons. So a double bond consists of 1 sigma bond and 1 pi bond. The sigma bond is going to be formed by an overlap of the sp2 orbitals on each carbon. The pi bond, this bond here, which is going to be above and below the plane, is formed by an overlap of the unhybridized p orbitals. So another way to notate this is that the sigma bond is formed by an overlap of the sp2 hybrid orbitals, and the pi bond is an overlap of the p orbitals. Finally, with sp hybridization, you take an s orbital and just one of the 3 available p orbitals. So you have 2 orbitals in, you get 2 hybrid orbitals out. We call them sp hybrid orbitals because you took one s and one p orbital to mix together. That means these 2 orbitals are still going to be hanging out as unhybridized p orbitals that are available to form pi bonds. So here, when you hybridize the s orbital and one p orbital, you get 2 of these sp hybrid orbitals out. And if this was the carbon here, its sp hybrid orbitals would be pointing 180 degrees away from each other, because an sp hybridized atom is going to have a linear electron geometry. Here you see the picture of ethine, this molecule. So it's a carbon triple bonded to another carbon. And we know from just doing our normal analysis, each carbon is going to be sp hybridized. So they're going to form the bonds with hydrogen by using an overlap of an sp hybrid orbital with a hydrogen s orbital. So that's shown here. Then notice there's a triple bond between the carbons. So whenever you have a triple bond, you have 1 sigma bond and 2 pi bonds. You can only ever have 1 sigma bond between 2 atoms, but you can have 1 or 2 pi bonds. So the sigma bond is shown here. It's formed by an overlap of the sp orbitals on each carbon. The other 2 bonds in the triple bond are pi bonds. And remember, when you have an sp hybridization, you have 2 sp hybrid orbitals and 2 p orbitals. So each carbon has 2 p orbitals that will overlap with each other to form the 2 pi bonds. So here we've got the p orbitals overlapping, and then the other p orbitals, which are harder to see, also overlapping. Moving along to section 1.10, the hybridization of nitrogen, oxygen, phosphorus, and sulfur. I'm actually just going to focus on nitrogen and oxygen. Those are the most important for us. So we determine the hybridization just like we did with carbon by counting up the electron groups. If there's 4 electron groups, it's sp3. If there's 3, it's sp2. And if there's 2, it's sp. Let's take a look at methylamine, which is shown here. So what is the hybridization of the nitrogen? What orbitals does nitrogen have? How are these involved in bonding? And where is the lone pair of electrons? So you could pause the video and see if you can answer these questions on your own right now. Then when you're done, click resume. So here are the answers. The nitrogen is sp3 hybridized because it has 4 electron groups. It has a bond to this hydrogen, a bond to that hydrogen, a bond to that carbon, and a lone pair. So that's a total of 4 electron groups. Anything that is sp3 hybridized must have 4 sp3 orbitals. How are those orbitals involved in bonding? Well, 2 of the 4 sp3 orbitals overlap with the hydrogen's 1s orbital to form those nitrogen-hydrogen bonds. Then a third sp3 orbital on nitrogen overlaps with the carbon's over here sp3 orbital to form the nitrogen-carbon bond. And then finally, where is that lone pair of electrons? Well, they must be in an orbital, and the only option is that they're in an sp3 orbital. What about the electron geometry? Since it's sp3 hybridized, it's tetrahedral. Now you may notice here the bond angles deviate a little bit from 109.5. That's just because that lone pair likes to take up a little bit more room. Now let's do another example with methanol, CH3OH, shown at the right here. And we're going to ask those same 4 questions. And the answers we get are shown in red. So oxygen has 4 electron groups, 2 bonds, and 2 lone pairs. So therefore it must be sp3 hybridized. If something's sp3 hybridized, it has 4 sp3 hybrid orbitals available, which also means it doesn't have any unhybridized p orbitals. How are those orbitals involved in bonding? Well, two of the sp3 orbitals are going to be overlapping with the carbon and the hydrogen to form those bonds. So an sp3 orbital overlaps with hydrogen's s orbital to form the OH bond here. And then the oxygen sp3 orbital overlaps with one of the carbon's sp3 orbitals to form this bond. Then what about those two lone pairs? Well, I've accounted for two of the four sp3 orbitals for oxygen, so the two lone pairs will then be occupying the two sp3 orbitals left. And what about the electron geometry? Again, it's tetrahedral because it's sp3 hybridized. Moving along to molecular orbital theory, I will just briefly describe this. So we've been using what's called valence bond theory, where we actually discuss hybrid orbitals and how they overlap to form bonds. But there is another way of describing how atoms bond and how molecules are formed, and that's called molecular orbital theory. And it's a description of covalent bond formation as a result from the combination of atomic orbitals to form what are called molecular orbitals. So whereas we thought of hybrid orbitals as belonging to an atom, in molecular orbital theory we think of orbitals that belong to the whole molecule. And in this theory, there are two types of molecular orbitals, bonding and antibonding, and they are just like what you might imagine. Molecular bonding orbitals contribute to bonding, and they are lower in energy than the atomic orbitals from which they formed. And antibonding molecular orbitals are higher in energy and will end up with the breaking of bonds. Here's a schematic with the simplest possible example of the H2 molecule. So if you take the two 1s orbitals from each hydrogen atom, you could combine them to form two different molecular orbitals. One would be considered the bonding orbital, and one would be the antibonding molecular orbital. So from this type of theory point of view, you would have both of the electrons available in the bonding molecular orbital, and nothing would be in the antibonding molecular orbital. The final topic is drawing chemical structures. So in Gen Chem, you practice drawing Lewis structures. We also often draw molecules in what's called a condensed structure, where we don't draw out all of the CH or CC bonds. And if we look at something like amoxicillin, if we draw the Lewis structure, so we're drawing in all of the bonds and all of the lone pairs, it starts to get really impractical when we do this for larger molecules. But if we were just to use the condensed formula, we would not have a lot of information about the shape of the molecule. So instead we use what are called bond line structures, also called skeletal structures, because they're just easier to read and draw. And this is what we'll be using throughout the rest of organic chemistry. So this is the Lewis structure, and this is the bond line structure. So what is the difference that you notice between the two? Well, first of all of the hydrogens have been omitted, and also all of the carbons have been omitted. So we don't draw out the carbons and the hydrogens in bond line structures. However, the nitrogens and the oxygens, those are still shown. And the lone pairs aren't shown. Sometimes people draw on the lone pairs on bond line structures, sometimes they don't. So bond line structures are the benchmark representations for organic compounds. Once you learn how to draw these, you can really impress your friends and family. So let's go over the rules for reading bond line structures. So each corner or endpoint represents a carbon atom. So if we look at this first example, there's a carbon atom here, 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 and here. So also if we look at this alkene, this double bonded structure, there's a carbon here, 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 and here. And then finally, there's a carbon at 1, 2, 3, and 4. The zigzag format, this format here, is fairly accurate in representing bond angles for sp3 and sp2 hybridized atoms, but for sp hybridized atoms, such as carbons 2 and 3 over here, you want to show a linear straight line format. Notice the hydrogen atoms bonded to each carbon are not drawn. So how do you figure out how many hydrogen atoms are on each carbon? It's just a matter of deduction. So you know that carbons want to form 4 total bonds. So you look at the number of bonds that are represented, and then you add the appropriate number of hydrogens to get to 4. So if we convert this structure to here, we do so by first adding in our carbons, and then notice with the carbon on the left here, it just has 1 bond shown to the carbon to its right. So it wants 4 bonds total, so it must need 3 hydrogens. Now what about the carbon double bonded to the oxygen? It already has a total of 4 bonds, 2 to the oxygen and 1 to the carbon on either side of it, so it's good. What about the carbon highlighted in green? Well, the bond line structure indicates 2 bonds to the carbon on either side. The hydrogens are omitted, so you would add 2 hydrogens to get to a total of 4. Same for this carbon, and for this carbon it would be 3 hydrogens. So soon this will become second nature to you, and you can just look at a bond line structure and know and understand how many hydrogens exist but just aren't shown. So for practice, why don't you try identifying the location of the carbons and hydrogens in all of these molecules, and then you can pause the video and check back and see if you had it correct. Okay, so let's start with this one. So there's a carbon at the end of each stick and at the intersection of lines. So there's 1, 2, 3, 4, 5, 6 carbons. And then we want every carbon to have a total of 4 bonds. So that would require 3 hydrogens on this carbon, 2 hydrogens here, 2 here, 2 here, 2 here, and 3 here. And again, you're not going to draw in your hydrogens all the time. This is just to help you understand where the hydrogens are that aren't shown. Soon it will become second nature to you. So there's a carbon here. So at every endpoint, at every intersection. And then if we start with the carbon on the left, it just has 1 other bond shown, so it must have 3 hydrogens. Same with this carbon. This carbon must have 1 hydrogen. This has 2, 2, 3. Okay, over here we've got carbon here, 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 and here. And then we can add in our hydrogens to get to a total of 4 bonds for each carbon. Okay, and then finally the last one. So we've got carbon here, 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 and here, here, right here, all along this ring, and then at those ends of those sticks. So we've got a lot of carbons in this, and now we just need to add in the hydrogens. So this carbon is going to have 2 hydrogens. This carbon will have 1 because it has a triple bond to the other carbon, so that's 3 out of the 4, so it just needs 1 hydrogen. This carbon isn't going to have any hydrogens because it's already triple bonded to the other carbon and single bonded to the one above it. This carbon also won't have any hydrogens because it already has 4 bonds. This carbon won't have any hydrogens because it already has 4 bonds. This carbon will need 3 hydrogens, as will this carbon. I know this is getting a little crowded. These two carbons don't need hydrogens, they're good. This carbon needs 2, this needs 1, and then these need 3. So what you're looking for here is first to identify where the carbons are, then make sure that each carbon has a total of 4 bonds. If 4 bonds aren't shown, you make up for the lack of bonds with hydrogens. So if you're given a Lewis structure or a condensed structure, you must also be able to draw the corresponding bond line structure. So rule number 1, sp2 and sp3 atoms should always be drawn in a zigzag format. Rule number 2, when drawing double bonds, draw them as far apart as possible. So this is much nicer than this. Remember that this carbon is sp2 hybridized, so the bond angles should be 120 degrees, but this drawing does not accurately show that, so this one is not right. When drawing single bonds, the direction in which you draw them is irrelevant. So this structure is the same as this because these single bonds can freely rotate. Rule 4, any atom other than carbon and hydrogen is indicated, as well as the hydrogens attached to them. So if we convert this structure to a bond line structure, we still draw in the oxygen and the hydrogen bonded to that oxygen. And the cardinal rule, number 5, never draw more than 4 bonds to a carbon atom. That violates the octet rule, which is an absolute rule for second row elements. Now let's practice drawing bond line structures. So we have a condensed structure here. We have 3 carbons followed by an OH. So that's going to look like this. So each intersection is a carbon, and then the carbon on the left would have 2 hydrogens, the next carbon would have 2, the next carbon would have 2, just like that. But just to draw the bond line, you omit the hydrogens and the carbons. Now let's try the next example. So to convert this compound to a bond line structure, we do the same thing. So we've got 1, 2, 3 carbons. So 1, 2, 3. I'm using the zigzag, and then I'm going to draw in my nitrogen atom and the hydrogens attached to it. A lot of times bond line structures are drawn, but not all of the lone pairs are drawn. So it's important to be able to identify lone pairs. So the way you do this is if you have a bond line structure and you have an atom with no formal charge, in the next chapter we'll talk about formal charge. What you want to do is figure out how many valence electrons it has. You can do this by just looking at the group number in the periodic table. Then you count up half of all the electrons in its bonds. If the number equals the valence number, you're done. If it's less than the valence, then you add lone pairs to reach the valence. So if we try this with ammonia, NH3, nitrogen has 5 valence electrons because it's in group 5. Here it has a total of 6 electrons in all of its bonds because it has 3 bonds and each bond has 2 electrons. We divide that by 2, which gives us the number 3. Therefore, it is short 2 electrons from its valence number 5, so we must add a lone pair to the nitrogen atom. Let's also try that with water. So water, the oxygen atom has 6 valence electrons. Here, there's a total of 2 bonds shown, which accounts for 4 total electrons, which when divided by 2 gives us the number 2. So oxygen is short 4 electrons, so we have to add 2 lone pairs, just like that. Let's practice this. So let's add in the lone pairs on the nitrogen and the oxygen, and then go through and add in all of the hydrogens. So first let me reiterate where the carbons are. So they're at each endpoint and intersection. So that's where all my carbons are. I'll go ahead and add in the hydrogens and then we'll look at the lone pairs. So the carbon on the left has one bond to another carbon. So to get to 4 bonds, we need to add in 3 hydrogens. Same with this carbon. The next carbon already has 3 bonds shown, so it just needs 1 hydrogen. This carbon is missing 3 bonds, so it needs 3 hydrogens. The carbon bonded to the oxygen already has 4 bonds, so it doesn't need any hydrogens. And then finally, this carbon on the right just has 1 bond shown, so it needs 3 hydrogens. Now let's look at the oxygen atom there. Oxygen's in group 6. It has 6 valence electrons. Half of all the bonding electrons shown, because it has a double bond, it has 4 bonding electrons. So half of that would be 2, meaning it's missing 4 electrons, so we can add those as 2 lone pairs. The nitrogen shown here has 3 bonds. It's in group 5, so it has 5 valence. Half of its shared electrons is the number 3, so it's 2 shy of the 5. So we need to add in 1 lone pair on the nitrogen. So your next steps are to read the assigned sections from the book if you haven't done so already. Then come to class with your questions ready. And finally, I've posted some practice problems from Chapter 1 in OWL that you can try.